The key word you want to think about with integration is accumulation. It could be dollars, it could be water, either tide coming in or a tank that's leaking. It could be revenue. I think the most tangible for most of us is the notion of accumulating distance. Like if we had a function of velocity and we wanted to accumulate distance, we could do this graphically by considering a 40 mile an hour velocity function. We've got somebody moving along at 40 miles an hour for a fixed amount of time. Our units, if we calculate the area of this, notice that we've got 40 miles per hour times 3 hours. The hours cancel out and we have 120 miles. Okay. The 120 miles is our time from time 0 to time 3. In geometry, you were never allowed to use the notion of a negative area. However, if you were to think about the distance of accumulation from time 3 to time 0, that would actually be negative 120. And the other thing you could consider is what happens if the velocity were under the curve. If we were going, let's say, negative 10 miles an hour, then our accumulation over time would be a negative distance. To really, if we were to go backwards in time, if we were going at a negative velocity from time t equals 2 to time t equals 0, it's essentially a negative of a negative. It's double negative, and we would actually get a positive distance. Let me put this into a different context. First of all, the big takeaway is you got to have, for this kind of analysis, you have to have a measurable geometric shape. Consider this situation here. Can you count, if we are starting at a location on an x-axis, and this describes our velocity, and our velocity is inches per second. Where are we after 6 seconds? There are geometric, fortunately I rigged this with a bunch of geometric shapes that you should be able to get our destination. First of all, recognize that we've got ourselves a rectangle, we've got a triangle, this is the rectangle, this is the triangle, and we've got a semicircle right here. We have 3 components of our movement that can be added together. So this rectangle, length times width, if you can't read it, it's 4 inches per second times 2 seconds, which this is 8 inches. The second item that we've got is a triangle. The triangle is 1/2 the base times height. If you can't read it, this height is 4, this base is 2, so we have 4 inches. And then finally, we've got this half circle right here. So area 3 is 1/2 and then pi r squared. Well, our radius here, if you can't read this, this is a radius equal to 1. So we have 1/2 pi times 1 squared if you want. So this is pi over 2. Okay, so where are we after 6 seconds? Well, we moved forward 8, and then we moved it forward another 4, and then we moved backwards pi over 2. So our displacement from where we started is actually going to be 12 minus pi over 2. So we did forward a bit, we did backward a bit. What's the distance traveled? Well, the distance traveled doesn't care whether we're going forward or backward. We take the absolute values of each of these areas, and we're fine with the 8, we're fine with the 4. This would be an absolute, so this would be 12 plus pi over 2. And there is a difference between displacement and distance traveled. Imagine you're on a track and you want to run the mile. 4 laps around, I think, is a mile. Well, the distance you traveled is a mile. However, your displacement, you ended up where you started with, so your displacement is actually 0. All right? So this notion of area is where the basis is for integration. Wow, I am so behind on time. Okay, suppose we were to do an approximation. Let's consider the curve negative x squared plus 3x plus 8. We don't have rectangles or triangles or circles. There are no geometric shapes that define portions of this. So what we're going to do is we're going to consider an approximation. And the approximation we're going to be using is a bunch of rectangles. Suppose we wanted to estimate the area, and we're looking from 0 to 8, and we want this area as an approximation. Well, our first course of action might be a rectangle, but how high does the and also, we've also got 4 subregions. So we're going to go with 4 rectangles. So hopefully you can see we've got our first rectangle resides here, but the question is, how high do we take it? I mean, do we go to I can see there's a left edge here. Maybe that's the height of the rectangle. On the other hand, there's a right edge over here. Maybe that's the height of the rectangle. Well, that kind of a decision is actually a strategy that you have to make when deciding which way you're going to approximate the area. If we were to do a right rectangular, my AP folks are going to call it a right Riemann sum. Your textbook is going to call it a right rectangular approximation method. This is what I tend towards because I've only been using the College Board this year. I tend to go with the textbook, which is right rectangular approximation. So if we're going to estimate based on the right edge, then our first rectangle is going to be right there. And I hope you can see that we've got a little bit of an overestimate going on. Our second rectangle will go to right there. Our third rectangle, if we're using the right edge, it's only going to go as high as this right edge takes us, which is right there. And then our third rectangle, our fourth rectangle, this is 2, this is 3. And notice our fourth rectangle has a height of 0. So our fourth shape, it's way down there, it actually ends up being nothing. So our calculation for this would be, we're going to do height times base. Well, the base, fortunately I picked very convenient numbers that we can use. I'm going to use a base of 2, since this is from 0 to 8, and we're doing 4 subintervals, each of our bases is equal to 2. And I already worked out the height of this function at various locations. So a right rectangular approximation. Our first area would be a height of 12 times 2. Our second region would be also a height of 12 times 2. Our third region would be a height of 8 times 2. And our fourth region would be a height of 0 times 2. And if you sum those up, you're going to get a right rectangular approximation. I got 64. All right? If we were to do a left rectangular approximation, instead of using the right edge, we're going to use the left edge. So our left rectangular approximation, we'll use our first area is going to be 8 times 2. Our second would be 12 times 2. Our third would be another 12 times 2. And finally, our fourth region actually does have area this time. It's going to be an overestimate, and I am getting a value of 8 times 2. And what that's going to sum to when I did this was I got a value of 80. These are approximations. There's another type of rectangular approximation we're going to do, which is called trapezoidal. Trapezoidal is if you were to, instead of making rectangles, you just make a bunch of trapezoids to represent the area under the curve. And your area for a trapezoid is you average the two heights. If this is height 1 and this is height 2, the average height would be height 1 plus height 2 over 2 times the base. And again, if you have these values all figured out, it's just a matter of plugging and chugging the right ones. Okay? There's another type of, oh man, I'm scrambling all over the place. I should stick to the script. Besides right and left rectangular, you can also do what's called a midpoint rectangular approximation. That is, instead of using the edges of the rectangle, for example, suppose we had the rectangle between 0 and 2. Well, instead of using the left edge 0, the right edge 2, you use the midpoint, which would be a 1. And if we were to use 1, hopefully, if this were the 1 and we rise to a height of here, hopefully you can appreciate that we've got a little bit of an overestimate here offset by an underestimate there, and the mid approximation generally is going to be your most accurate. So we've got rectangles, mid, left, and right, and we've got trapezoids. Your textbook has something called Simpson's method, which I have not seen the College Board talk about yet. It may be coming. I'll have to fill in the gaps if the College Board doesn't mention Simpson's method. All right, so finally, let's do this. What is the actual area under the curve? Let me show you we are not just about approximations in here. The way you would get this area is with something, those of you that have physics right now, you've already seen integration. This is the symbol that represents that we are integrating. We're summing a bunch of rectangles. And our bounds, we are bounding this from 0 to 8. So this is our lower bound. This is our upper bound. And what we are integrating is called the integrand. And that's where this function goes in. We've got negative x squared over 2 plus 3x plus 8. So we've got most of the components. The final thing we need is what's called the variable of integration. That tells us which direction these rectangles are going. What that means is that sometimes we're going to have situations where it might be easier to make horizontal rectangles instead of vertical rectangles. For the immediate future, we're just going to be making vertical rectangles, which means our variable of integration is almost always going to be dx. I'll let you know when it switches, all right? So the process for integrating this function and getting the actual area under the curve instead of an approximation, for right now, we're going to be using what's called the power rule of integration. It's basically the power rule of differentiation, but backwards. The general form of it is if you have x to the n, your integral of that is x to the n plus 1 over n plus 1. So applying this to this integral, what we would have is negative x to the third over 2 times 3. The negative and the 2 are just along for the ride. And then our next term, this integrates to 3 times x squared over 2. As far as a constant goes, just imagine it as like x to the 0 power. Then if you imagine this as x to the 0, then the integral of this becomes plus 8 times x to the 1 over 1. We don't really need the 1, but there you go. Now to evaluate this, what you're going to want to do is you put a big bar at the end, and you're integrating from 0 to 8. So what you do is you start off by taking your upper bound and put that in everywhere you see an x. So the 8 goes here, it goes here, and it goes there. And then what you do is this is the upper bound, and then you subtract off the lower bound, which in this case it's 0, so you would put 0 in wherever you had an x, so the lower bound. And what you end up with this one, if you integrate it, it's really messy. It ends up being 224 over 3. Or about, let's see, what did I have? 74 2/3. So the left approximation was an overestimate. The right approximation was an underestimate. This is the exact value that's under the curve. All right? I'm at about 10 minutes to go. Okay. Let me go to the connection between these approximations and the actual integral. Give me a second here. Okay, we want this area of this function from A to B. First of all, we're going to divide this up into partitions. And we're going to, just like before, we're going to choose 4 partitions. So this we're going to call x1, x2, x3. And just for completeness sake, this is actually going to be x4, and this a would be x0. The distance across of all these is delta x. And if all of these partitions are the same, what you end up with is delta x is equal to b minus a over the number of partitions you have. Basically, here to here, and you divide it. How many do you want? So, to try to put this in the context of the rectangles that we're working with, the first rectangle, this one right here, well, what is x sub 1? How did we get there? Well, the way we got there, x sub 1 is equal to, well, we got to there by going to A and then adding on a single delta x. Okay, that's how we got to here. How do we get to there? Well, x sub 2 is equal to A plus delta x times 2. It's 2 of these. We've gone 1, we've gone 2. X sub 3 is A plus delta x times 3, and x sub 4 is equal to A plus delta x times 4. So those are the actual heights that are the x values along the way. So our summation for this is going to be f of a, I'm just going to, I don't have time to write it all out. F of x1 times delta x plus okay, it's just a lot of rectangles. Don't let the syntax intimidate you. All right. Now, one of the things I hope you can see is that there's a lot of redundancy in what I wrote. For example, we could have factored out the delta x. Well, there's a consolidated way in which we write this, and that's with what's called a sigma notation. The sigma notation, this is the Greek letter sigma, which means sum. And what you're summing is you've got to tell it, well, okay, what am I summing? Well, you have to start somewhere and you have to finish somewhere. And then you have to actually think about what it is you're summing. So suppose I were to start at I equals 1 and I want to go to 4. Okay, and let's start with an easy one. Suppose I'm summing up i's from 1 to 4. This is where you start, this is where you finish. So your first element is going to be I equal to 1. And then what happens is this is like a loop in a computer program. It just loops through. It always goes up by 1. And it stops when you hit 4. So as we continue with our second loop, we're going to go from 1 to 2. So this would be plus 2. Well, we haven't hit 4, so we do it again. Well, the next increment would be plus 3. Haven't hit 4, do it again. And then plus 4, we hit 4. This is what tells us to stop. So we stop and we're done. This is actually a representation of the number 10. All right? So, if you were to do, let's say, 3i squared, well, that would be 3 times 1 squared plus 3 times 2 squared plus 3. Okay, and these tend to get complicated, all right? So let's put this in the context of our Riemann sum. Okay, a couple of things I can do is, first of all, this is f of a plus delta x times I times delta x. Okay, what I did is these x1, x2, x3, and x4 are all represented by there. And what's toggling is how many increments of delta x, how many rectangles are we moving over? Here's our first one, here's our second, here's our third, here's our fourth, here's where we stop. This is a representation of a right Riemann sum. On balance, you can consider this expression. When you're looking at a Riemann sum, you can consider this to equal the x. You can consider this to be equal to the delta x or dx as you evaluate this. Now, in order to have accuracy, what we've got to do is we have to have an infinite number of these. So the extension that we're going to put on this is, hopefully you're recognizing a limit expression. We want the limit as n goes to infinity of I equals 1 to n. Now we're not stopping at 4. Instead, we're doing an infinite number of these horizontal rectangles, or vertical rectangles, and this is the same statement. F of A plus delta x I delta x. And one of the things, when I asked you guys to do that paper cutouts and matching, I want you to think about how you could translate between this and the definite integral, which goes from a to a plus something, f of x dx. And I have 3 minutes left, so let's go through a couple of examples. I'm going to try not to tip the computer over as I slide us down. Okay. Can I do this? I need a cameraman. All right. I hope you can read that. Maybe I should use a different color. This is a Riemann sum. What is the definite integral that translates to it? What you want to look for, first of all, is this is almost always going to be your delta x. And remember, that's equal to b minus a over n. So since we've got the n's, our b minus a, our difference between the upper and the lower bound is equal to 3. So I could start by saying this goes from a to a plus 3. Well, we can do a little bit better because we know the expression, the general form for the x is going to be a plus, oh my God, what is it? 3 over ni. This generally is going to be your form for your x. So there it is right there. This is the a value. So we can do better than saying we start at a. Instead, we can say we start at 2 and go to 5. This is our x value, and since it's inside of a sine function, this is the sine of x dx. And this is the definite integral that equates to that Riemann sum. Okay, how about this guy? Okay, I see that we're going to have a difference of 5 between the upper and the lower bounds, but where do we start? Where's the a value? Think about it as 0 plus. All right, now what we've got is we've got our integral. We start at 0, and our difference between our upper and lower bounds is 5. And the function that this x resides in is a squaring function. So this would be x squared dx. And this would be the translation of that. All right, now here's where you earn your paycheck, is with this last one. And I know I'm pressing time, but I would encourage you to stay with me on this. I am recording it, so if you've got to go, I understand if you have another class. We have a discrepancy here. Notice we've got a difference between, we've got a 6 over n and a 3 over n. These things got to be the same in order for us to translate to a definite integral. Well, one of the things I could do is I could just multiply this 2 times this 3, and what I end up with is 10 plus 6 over ni times 6 over n. And that translates pretty easy enough to the integral from 10 to 16 of, it looks like just 10, or just x dx. And that's it. But on the other hand, this is where it gets tricky, and I got you for 1 more minute. Suppose I did this. Suppose instead of multiplying this 2 across to that 3, what if instead I factored a 2 out? I factored a 2 out of that middle part. Instead, I could end up with this. I could have 4 times 5 plus 3 over ni, 3 over n. All right? That would translate to the integral that would be this. It would be the integral from 5 to 8, And the function that we're integrating is 4x dx. So the conundrum and the frustration that you're going to see in the early part is that we have translated to this integral and we've translated to that integral, and they are both valid representations of the same Riemann sum. And in fact, if you integrate both of them, I have it somewhere, they both end up equaling 78. Wow, I'm 1 minute over. I'm going to close the recording right now. I'm afraid to see how many of you guys are still left. This will be posted on Schoology if you want to rewatch. I really packed a lot in there. Thanks for hanging with me. I wish you guys were here. Bye.